Hello everyone, myself Dr. N.CH.Ramgopal, working as Associate Professor in Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on Residue Theorem Part 2. In the last session, I have introduced the Cauchy's residue theorem, using which we can evaluate the line integral of the given function by finding the poles and corresponding residues. And here the main point is to identify the poles which are within the given circle C. Then by Cauchy's residue theorem, the line integral is equal to 2 pi I into sum of the residues. So find the poles, identify the poles which are within C and find the corresponding residues, and use the Cauchy's residue theorem to evaluate the given line integral of the function f of z along the curve C. So let us solve some more problems on the same. Here we need to evaluate the line integral along the curve C z minus 1 equal to using Cauchy's residue theorem. So coming to the solution part, the given line integral is dz by z square into sin hz. So here the curve C is mod z minus 1 equal to 2. And first we need to find the poles of this function. How to find the poles? By equating the denominator to 0. So z square into sin hz is 0. That implies either z square is 0 or sin hz is 0. So z equal to 0 is a pole of order 2. It is repeated twice. So, and also sin hz is 0. That implies sin will be 0 if the angle is 2n pi. So z equal to 2n pi, where n equal to 0 plus or minus 1 plus or minus 2 and so on. That means n belongs to the set of integers z. And here already z equal to 0 is a pole of order 2, and here again it is repeated. Therefore, z equal to 0 is a pole of order 3. And also it is very clear that z equal to 0 only lies inside the given circle mod z minus 1 equal to 2. For all the remaining n values, the points lies outside the circle. So to apply Cauchy's residue theorem, we need to identify the poles which are within C, and then we find the residues of those poles. So here z equal to 0 is a pole of order 3. So we need to find the residue of z equal to 0, residue of the function at z equal to 0. To find the residue, there are two ways. You can use the formula, the standard formula, or else we can use the Lorentz series expansion. Let us use the Lorentz series expansion of the given function here. So here f of z is 1 by z square into sin hz. So what is the expansion of sin hz? Z cube minus, it starts with z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial and so on. So this is equal to 1 by z square into, take z common here, then 1 minus z square by 3 factorial, z power 4 by 5 factorial, z power 6 by 7 factorial and so on. Now this is equal to 1 by z cube into, by taking this term to numerator, we get 1 minus z square by 3 factorial plus z power 4 by 5 factorial minus z power 6 by 7 factorial and so on. So this is 1 by z cube, 1 minus, taking minus sign common here, z power 4 by 5 factorial plus 6 by 7 factorial minus and so on. Now this is having power minus 1. So 1 by z cube, now using the standard expansion, 1 plus z square by 6 minus z power 4 by 120 plus so on, minus, all the terms are positive. So z square by 6 minus z power 4 by 120 plus so on whole square plus so on. Now multiply with this 1 by z cube plus 1 by 6z minus z by 120 plus and so on. So this is the Lorentz series expansion of the given function, and the residue of, what is the pole here? Z equal to 0. The residue of f of z at z equal to 0 is the quotient of 1 by z in Lorentz series expansion. This is the Lorentz series expansion, and here 1 by 6 is the quotient of 1 by z. So the residue is 1 by 6. Now by Cauchy's theorem, residue theorem, the line integral of the given function is equal to 2 pi I into sum of the residues. Here we have only one residue, so 1 by 6 into 2 pi I. So the integral is equal to 3 pi I. Now coming to the second problem, here the given circle is mod z minus 1 equal to 1, and find the line integral using residue theorem. So let us find the poles. By equating the denominator to 0, here we get z equal to pi by 2, which is a pole of order 3. Now we need to find the residue of f at a pole of order m. The formula is 1 by m minus 1 factorial limit z tends to a d power m minus 1 by dz power m minus 1 z minus a power m into f of z. So here residue of f at z equal to pi by 2, which is a pole of order 3. So a equal to pi by 2 and m equal to 3. So 1 by 2 factorial limit z tends to pi by 2 and d square by dz square of z minus pi by 2 whole cube into z cos z by z minus pi by 2 whole cube. So here these two gets cancelled, and we need to differentiate this z cos z twice. So 1 by 2 limit z tends to pi by 2 d by dz of z cos z. So differentiating the first time, limit z tends to pi by 2 d by dz of z cos z. UV rule, here the first function is z, second function is cos z. So by applying UV rule, z into derivative of cos z minus sin z plus cos z into derivative of z is 1. So 1 by 2 limit z tends to pi by 2 d by dz of cos z minus z sin z. This is the first derivative. Similarly, we need to differentiate it again. So the residue is 1 by 2 limit z tends to pi by 2 d by dz of cos z minus z sin z. So that is 1 by 2 limit z tends to pi by 2. Now the derivative of cos z is minus sin z minus derivative of z is 1. So sin z minus z into derivative of sin z is cos z. So which is half limit z tends to pi by 2 minus 2 sin z minus z cos z. Now taking the value z equal to pi by 2. So as limit z tends to pi by 2, replace z by pi by 2 minus 2 sin pi by 2 minus pi by 2 into cos pi by 2. We know that sin 90 is 1 and cos 90 is 0. So here we get 1 minus 0. So the answer is minus 1. And now by residue theorem, the line integral f of z dz is 2 pi I into sum of the residues. Here we have only one residue. So 2 pi I into minus 1 minus 2 pi I. So the line integral of the given function is equal to minus 2 pi I. So like this, with the help of Cauchy's integral theorem, we can evaluate the line integral of the given function along the given curve. Let us solve another problem. Here we need to evaluate the line integral where C is the circle mod z equal to 4 using Cauchy's residue theorem. So let us consider the given e power z by z square plus pi square whole square dz. So this is line integral e power z by z square plus pi square can be written as z square minus I pi whole square. So which is e power z by z square a square minus b square. So a minus b z minus I pi into z plus I pi, and we have square for both. So first we need to find the poles by equating the denominator to 0. Z square minus I pi whole square is 0. So z square equal to I square pi square. So z square equal to minus or else here z equal to plus or minus I pi. So z equal to plus I pi and z equal to minus I pi are the poles of order 2. So here m equal to 2. Now the residue of f at the pole z equal to I pi. This R1 can be calculated using the formula 1 by 2 minus 1 factorial, because m equal to 2, limit z tends to that I pi d by dz of, and this I pi is the pole for this z minus I pi whole square e power z by z minus I pi whole square into z plus I pi whole square. Now this is 1 by 1 factorial, which is 1, limit z tends to I pi, the derivative of these two gets cancelled, e power z by z plus I pi whole square. So we need to differentiate this twice. We need to differentiate this with respect to z. Limit z tends to I pi. So we apply u by v rule, and the denominator is z plus I pi whole power 4. Denominator whole square, denominator into numerator derivative e power z minus e power z into denominator derivative 2 into z plus I pi. Now this is equal to limit z tends to I pi. Here we can take e power z 2 plus z plus I pi common, e power z into z plus I pi common, and what remains in the first step? Z plus I pi, then minus 2 by z plus I pi power 4. So this 3 times, and by applying z tends to I pi, e power I pi into I pi plus I pi minus 2 by I pi plus I pi whole cube. So this is e power I pi 2 I pi minus 2 by, this is 2 I pi whole cube. So 2 into e power I pi minus 1 by 8 into I cube pi cube. So R1 equal to 4 times e power I pi into I pi minus 1 by I cube. It can be written as I square into I. So, minus I pi cube. So, this is e power I pi into 1 minus I pi by I into pi cube. What is e power I theta? Cos theta plus I sin theta. So, e power I pi is cos I pi plus I sin, cos pi plus I sin pi. Sin pi is 0. So, cos pi, which is minus 1. So, therefore, this is minus 1 into 1 minus I pi by I pi cube. So, if you multiply with minus sign, minus I pi by I pi cube. So, R1 is I pi minus 1 by I pi cube. Multiply with I on both numerator and denominator. I into I pi minus 1 by I square pi cube. So, R1 is I square pi minus I by I square is minus 1. So, minus pi cube. So, this is minus common I plus pi by minus pi cube, which is I plus pi by pi cube. Pi plus I by 4 pi cube. Now, similarly, you can calculate the residue of the function at the other pole minus I pi. So, residue of f of z at z equal to minus I pi. Simply, we will get replace I by minus I. So, I by minus I. Then we get pi minus I by 4 pi cube. Or else, if you want, you can calculate also, you will get the same. Now, by residue theorem, the line integral of f of z dz is 2 pi I into sum of these two residues, R1 plus R2, which is pi plus I by 4 pi cube plus pi minus I by 4 pi cube. So, here 2 pi I into pi by 4 pi cube. So, 2 pi by 4 pi cube, and the line integral of the given function is equal to 2, 2, 4 gets cancelled, pi, pi, and here this cube cancel. So, the answer is I by pi. Hence, using the Cauchy's residue theorem, we can evaluate the line integral of the function by finding the poles and residues. And here the main point is to identify the poles which are within the circle C. And the theorem states that 2 pi I into sum of the residues. The line integral is equal to 2 pi I into sum of the residues. So, this is for today's session, and we will meet in the next session. Thank you.